Hi guys, so this is video 3.2 for exponential models, and it's going to be starting with a very important concept with the fact that we have four main equations that we use when dealing with exponential models, whether it's exponential growth or exponential decay. So the first one is P of t is equal to P times 1 plus or minus r raised to a t power. So this is for population growth and depreciation. You'll often see the terms population, and that's why it's in terms of P versus X or Y or so on and so forth. So P of t is what you hope to get. P is your initial value. Rate has to be changed from a percent to a decimal, and your t is going to be time in terms of years. This 1 plus or minus r is if you have an exponential increase, it's going to be 1 plus r, and if you have an exponential decrease, it's going to be 1 minus the rate. The second formula is half-life, which is a is equal to a sub 0 times 1/2 to the t over k, where a is what you hope to get, a sub 0 is your initial amount, 1/2 is always going to be your constant base, and this time it's raised to your t, which is in terms of years or days or whatever it may be, divided by k, which is the number of days in a cycle. So if it takes the half-life of 20 days for something to have a half-life, then 20 would be your k value. For 3, it's P of t is equal to P times e to the RT, where P is your initial amount, E is that 2.718 approximation, and R is your rate, again changed to a decimal, and T is time in terms of years. So this is when money is compounded continuously. Notice the word continuously. That is the only time that you use, we call it the PERT formula. The last one, P of t is equal to P times 1 plus R over N to the NT. P is your initial amount, 1 plus R is your rate, so you're going to change that again to a decimal, over N, raised to that same N times T in terms of years. So this is for when money is compounded in general, but there's different times that money can be compounded. So for example, if it's daily, N is going to be 365. So 365 would go here for N, and it would also be substituted here for N. If it was weekly, N would be 52, because there's 52 times that it would be compounded in a year. So 52 would go here and here. Quarterly would be 4, monthly would be 12, annually 1, semi-annually N would be 2. So for a couple of the problems where you might see some of these formulas come into play, that in 2000, the population, keyword population, of Guam was 279,000. Each year, the population has increased at a rate of 3.5%. What is the anticipated population for 2018? So population of T is equal to our population equation. In this case, we're using 1 plus R because it's saying that it increased at a rate of 3.5%. So when I substitute in my numbers, P is my initial amount, 1 plus R, which is going to be changed to 0.035, raised to a T power, which it says in 2018. That is 18 years since 2000, so that's why our X value, our T value, is 18. So if I put this into a calculator, I end up with 518,239.49 people. For the half-life of a radioactive substance is 10 days. If there is 20 grams initially present, how many days will it take to have 8 grams remaining? So we're using our half-life formula and subbing in the values that we have. We know that there's 20 grams initially, so that's my A sub 0. Our 1/2 doesn't change ever. It says how many days, meaning find out the time. Our K we talked about is the cycle of how long it takes for a half-life to go through. So it says that the half-life of a radioactive substance is 10 days. That means that my cycle is 10 days long. That's why 10 is substituted there. And we want to know when we have 8 grams remaining, which is why this is what I want it to be. Instead of solving this out algebraically, we're going to put this into y1 and y2 and find where they intersect. If you look on a graph, they end up intersecting at 13.22 days. And the last type of problem is Julie's deciding which savings account to put her money in. She has $1,000 to deposit, so determine how much money she will have after 10 years in each of the following accounts. So for A, it says an interest rate of 2% compounded continuously. So because of the word continuously, we want to use our PERT formula, which again starts with the initial amount. It's always the initial amount, but this time it's E raised to the RT. When we put this into a calculator, we end up with $1,221.40. Part B says 4.5% rate compounded quarterly. So if it's compounded quarterly, it's not continuously, we have to use that last formula. which is the initial amount of 1,000 times 1 plus the rate, which is changed to 0.045, divided by 4 because it's quarterly. That 4 is the same up here as well, and again it's after 10 years. So when I put this into a calculator, I end up getting $1,564.38. And lastly, it says compounded monthly. So again, a very similar equation to B and C, but instead of it being compounded quarterly where we used 4, we're using 12 because it's monthly. So 1,000 is your initial amount, 1 plus the rate, in this case it's 4%, so 0.04 divided by 12, raised to that same n times t, which we said was 10 years. And when I put that in a calculator, I get 1,490. So Julie should decide, because which one gives the most money, to invest her money in a compounded quarterly at a 4.5% interest rate savings account.